Next up, I want to talk about arrays. We've talked about arrays a bit, both with assembly and C code, but I want to talk about some of the ideas a little bit more explicitly. In C, we have two different ways to declare a variable that's going to have an array in it. The first way, we see kind of both ways in the main function. So let me go ahead and type that real quick. Int main, int argc, char pointer argv. So argv is a two-dimensional array. It's an array of strings, and then each string is an array of characters. So we can look at that as being, and we have two different notations for it. We have the pointer notation, and we have the square brackets without a number in it notation. Other examples of both of those, we could have, for example, int x's square brackets. So that's going to talk about an array called x's of unknown size. And we could have int pointer y's. So that's going to talk about either an array of integers of unknown size, or it could be talking about the memory address of a single integer. And it turns out that those are basically the same thing. In fact, if we have the memory address of a single integer, there's sort of absolutely no way to distinguish that from having an array of length 1. Those are the same thing. And when we go to write either of these things in code, we're going to get the same behavior either way. It's actually the same type. In fact, this thing, where we have the square brackets, is going to automatically do something that people sometimes talk about as pointer decay. So if we say int x's square brackets, the compiler is just going to go ahead and rewrite that as int pointer. So let's go ahead and look at a couple of code examples of arrays in action. And we'll go ahead and let's go ahead and just add up a list of numbers for the fun of it, just because we can. So, or add up a array of numbers. So, int main, int argc, char argv, and we're not going to use those, so I'm going to follow that convention where we're going to prefix the name with underscores. And then I'm going to say that char x's is going to be 1, 2, 3, 4. Char nn is 4. So we have an array of length 4. In this particular situation, we could do some trickery to discover the length of this array in our C code, but that's a bad idea. We want to avoid trying to treat arrays as being different from pointers. Let's make these ints. I don't know why I made them chars. In fact, let's make these longs to make it simpler in the assembly translation. Then I'll say 4, long ii is 0, ii is less than nn. We'll print out the sum when we're done, and then sum is going to plus equal x is ii. So 1 plus 2 plus 3 plus 4 is 10. And we get a segmentation fault. Let's go ahead and try to debug this. I'm going to start by just including the headers it wants. So that is only that. So then we have some warnings that we have excess elements in scalar initializer. So the syntax actually is that we need to have square brackets because that will do a stack allocated array. So this is one case where the syntax of a array and a pointer is slightly different, and it's that the C compiler can't understand what to do with this curly bracket initializer list unless the thing it's assigning to is an array, which is fine. So we can do it that way, and we can make some changes. As I mentioned in last week's lecture, this syntax here of x's and then II in square brackets is actually what we call syntactic sugar for the dereference of a pointer arithmetic expression. We're going to take x's and then add x's the pointer, this thing decayed to a pointer, and then we're going to add the integer II. So this is going to produce the memory address x's plus size of size of x's sub 0, which is a long, times II. And that should produce the same result. Still 10. And because addition is commutative, we happen to know that we could reverse those. We could say II plus XX. And that'll still work. And we can go one step further to II sub XX's. And that still works. It has to work because the array indexing decays into or gets translated into this pointer arithmetic syntax. Now, if we want to translate this into assembly, that's pretty straightforward. Let's go ahead and copy summary.c to summary.s. There's no multiple functions here, so we just have to translate the one function. Global main text, comment this thing out, data. So we have a format string, which is a string, which is %LD new line. That's the only string we use. All of these are equivalent, but we're going to go ahead and use that because there's a simple form that translates sort of directly into. So then we have our main function. Do any local variables need to survive a function call? No, there's only one function call, which is the printf. Now, unfortunately, enter 00 is... we're going to leave enter 00 here, and we're going to do an explicit alloca for x's here. So we're going to say sub RSP, 8 times 4 is 32. And I think the 32 comes first because the destination is going to be RSP. Now we can mov RSP over to RDI because x's is RDI. I'm going to make it RDX. X's is going to be RDX. Mov 4 into R10. NN is R10. Mov 0 into RAX. Sum is RX. Then we'll do our loop. So loop cond, loop done. RCX, so II is RCX. And then we need to increment RCX before we loop back, and there we have our basic loop except for the condition. The condition is going to compare R10 to RDX, R10 to RCX, so we're asking is II less than NN. If it's greater than or equal to, we're done. Otherwise, we're going to add. Now we need to add the value in memory at x's sub ii. So x's is rdx, ii is rcx, size of long is 8, and we'll add that to rax. Now all we have to do is print and we should have a thing. No pi o sa sum array.s that assembles sa, gives us a sum of some unreasonably large number. What did we get wrong? RDI, RSI, printf. Oh, we didn't fill in our values. We can do that. So mov 1 to 0 rdx, mov 2 to 8 rdx, mov 3 16 rdx, and mov 4 to 24 rdx. This is this initializer list, and that actually has to happen. There's no magic way that data can get in there unless we make it global and define it down in our data section, but that's not actually what the C code does, so we don't want to do that in our assembly. These need to be mov q's because we're moving 8 bytes. Now we run it, we get 10. There's one more variant I want to demonstrate here, and that is if we do this manually. So we want to calculate that address sort of by hand. And to do that, I'm going to go ahead and not use RAX as my sum. Instead, I'm going to use R11 as my sum, because we're going to use RAX in the multiplication to calculate the memory address. So we're going to start by moving RCX into RAX. Then we're going to do an imul. So we're using R10, R11. I guess we need to use R9 because we can't actually specify a constant here on imul. So I'm going to use R9 there. So that gives us this RCX times 8. Then we are going to add RDX to RAX, and then we'll do a mov of the thing at memory address RAX into another temporary, I guess we can use R9 again. And then we're going to do an add of R9 into R11. We don't need the temporary, we can just do the add. So that should, this code is doing in 5 instructions what this code does in 1 instruction. Might be a little bit slower, but it's logically the same, assuming I got it right. Run SA, and we get a segmentation fault. Let's debug this for the fun of it. So the value in RAX is 0. That's not quite right. R9 was 8. RDX is 0. Why is RDX 0? Because imul puts the high bits in RDX. Nice. So we can't use RDX as this, we'll use R8. try this again. All right, so that produces 10. I can run it without GDB. We get 10. Once I stop being silly with RDX, because that's not a register that's safe to use across IMUL, we get the expected behavior. So I think that's all I want to say at the moment about arrays. Arrays are one of the basic data structures that we have available in C, and arrays are enough to accomplish a lot of things, but not everything. So in the next video, I'll talk about the other kind of basic data structure we have in C.